What you see in front of you is the International Space Station, what I spent most of my professional life working on. A lot of us never thought we'd ever see this day, but we finished assembling this. We started assembling in 1998 and finished assembling it when the shuttle program retired in 2011. And it's been permanently manned. Humans have permanently been living up there for almost 15 years come December. So hard to believe that it's come this far. We're already on our 45th expedition. Just, I think 2 days ago, 3 more cosmonauts came down back to Earth, and now we're back to the normal crew of about 6. Most of them stay up there for about 6 months at a time doing research. You might have heard 2 of them are actually doing what they call a year in space, where we're trying to figure out what the effects of zero gravity are on the human physiological systems for a longer duration. If we're ever going to go to Mars, which everyone continues to talk about, and we've all had a desire to go there, at least in the space industry for decades, you're going to have to, it's take almost a year to get there. You have to be on the surface for a year and a half, and then a year and a half, about a year, 10 months to a year to get back. So interesting enough, there's one cosmonaut up there, Mikhail Kornienko, and then Scott Kelly. He's actually a twin. His twin brother was an astronaut as well, has since left NASA, but they're doing a twin study as well to see these effects. The space station is a partnership with these 5 space agencies, Canada, Europe, which is 11 countries, Japan, U.S., NASA, obviously, and then Russia. And these are all the flags of the countries around the world that participate in the space station. These are all the contributions of all the countries and the partnerships that they make, the U.S. being the blue color, and Canada contributes the robotic arm, the small green module here is from the Europeans, and then the Japanese have a large research module there. And the Russians, I always seem to draw them in red for some reason. I've never figured out why that is, but there's the Russian segment over there with their laboratories. Here's all the places around the world where the mission control centers and the launch sites happen that service the space station, so it's very international. This is a map of the world that shows where all the research and educational activities happen related to the space station. So Australia obviously participates in a lot of research and educational activities, even New Zealand over there. This is the official picture of the crew that's on board, but they also do a lot of informal things. A lot of the things I speak up about a lot when I travel is about science, technology, engineering, math. We call it STEM, trying to inspire the next generation of explorers. That's a big reason why NASA exists. And so they try to make these crew portraits a little more exciting. So we tried to get into the movie themes about 10 years ago. So they started with this one here, obviously The Matrix. And then we had Harry Potter was real big for a while. So this was STS-124 in the Order of Discovery. And then obviously that one harks back to the 60s. And then instead of the Brat Pack, we had the Right Pack. And then this one somehow snuck through. Somebody said this was Quentin Tarantino's first movie, these Reservoir Dogs. Not exactly a family-friendly movie. Somehow the PAO folks, the public affairs folks at NASA, approved this one. Not sure how. This one's a little obvious. Like Abbey Road, Expedition 26. You can see the Roman numerals there. And then Tron was a big movie for a while, and he's got the disc in his hand there. And then instead of the Transformers, we had the Transporters. And then, sort of like when the kids are in the backyard having fun, it's all fun and games until you sort of overstep that line, and someone gets hurt. So they kept doing this for a while, and then they went over the edge there. So instead of Pirates of the Caribbean, we have Pilots over the Caribbean. And I talked to a photographer right before I left NASA when I retired a couple years ago. I said, this is all done in Photoshop, right? And he said, no, they actually rented these costumes and had these guys dress up. And so from then on, they went back to more artistic interpretation. So that was sort of over the edge. A little bit about myself, what I did for the last 10 years of my career at NASA. We did qualitative risk management. We called it continuous risk management, and that actually coincidentally coincides 100% with the ISO 31000 risk management standard that actually people from New Zealand and you in Australia here were instrumental in writing. The other thing I did was quantitative, and this came out of the Nuclear Regulatory Commission after the 3 Mile Island nuclear accident in the U.S., and this is where we try to model quantitatively with hardware reliability for components all the systems of the space station, Over here, we try to do human effects of human error, and then medical research would tell us through longitudinal studies of looking at pilots and astronauts and people in Antarctica how often you get appendicitis or a heart attack and die, or a tooth infection or sepsis in the kidney, those kind of things. We also looked at phenomenological risks, which were very difficult to quantify, like fire on a space station that's hard to quantify, orbital debris. We also tried to do something nearly impossible called software risk, try to figure out what contribution software does. It's a very difficult field to try to quantify, and then all the visiting vehicles that could come up and potentially collide. The powerful thing about this was not only does it come up with a point value, but it gives you uncertainty. So if you're looking at two different options, you can say if one mean is a little lower than the other, you might think, well, that's a lower risk option. But if the uncertainty bands overlap, you'd say, well, risk really can't inform this decision, and you should make that decision based on cost or technical or some other availability concerns. But if the risk were to be a lot lower and there's not a lot of overlap with the uncertainty, you can tell yourself that that's probably a lower risk option there. The other thing is you can break down those means of that risk. For instance, this is the risk of evacuating the station or losing a crew member. You can break those down to say, well, the biggest risk of that risk is orbital debris, and then robotics and power systems, thermal systems, so it can be very powerful. I was going to talk about 3 case studies, but before I do that, I wanted to show you an important film that typifies the world-changing research and engineering that has come out of this well over $100 billion research facility in low Earth orbit. You can tell this was done about a year ago. You'll see by the theme it was done about a year ago or so. So we'll need some sound for this if we don't have it. So obviously that was for the World Cup last year, but we do more on the space station than just play. But I like to show that one for fun. But I did want to talk about 3 miniature little case studies I put together for you today that talk about the most serious of consequences, and that's, of course, the loss of life, which we worry about in the safety industry, and loss of life in a very public way. I'm going to present 3 human spaceflight accidents you should be very familiar with, all that happened during my 30-year career. And I'll try to look at not just the root causes, and I won't get too lost in the technical details, but look more at those generic things that apply to all of us in all of our industries, those human, management, organizational, and process-related causes. And of course, the point of this is always in our industry is to try to avoid future accidents, and that's why we do safety analysis, hazard analysis, system safety, risk management, is to avoid these future problems from occurring. So I'll try to cover not just what happened, but why it happened. So I needed a transition slide after that silly stuff. So that was my transition slide. Okay, so I'll talk about the Challenger accident in 1986, the Columbia accident in 2003, and then the recent accident happened less than a year ago with Virgin Galactic, Richard Branson's space company, where he hopes to send have a commercial airline type of thing for space tourism. Back to 1986, the Challenger accident. Of all the accidents I'm going to cover today, this is obviously one of the most disheartening and most avoidable of all the accidents. In 1986, the Challenger exploded, sending 6 astronauts and the school teacher, Krista McAuliffe, to their deaths. The public reaction was shock and disbelief. Americans had learned to expect routine shuttle flights from NASA. Some of the causes surfaced almost immediately, and they were very disturbing. The mission was supposed to be very symbolic in so many ways. It was supposed to represent the safety of spaceflight. After all, we were sending a normal, everyday teacher into space. and she was going to have, lessons for the school children, taught from outer space. Horribly, as thousands and thousands of children around the world tuned in, the Space Shuttle Challenger exploded 73 seconds into launch, and a lot of us here remember that day. The physical causes, of course, are well known. Here's some of the disbelief of the flight controllers. Here's a picture of Krista McAuliffe, and obviously you may remember People magazine. I'm sure you had People magazine here, and some training. And of course, the physical causes was the famous O-ring of the solid rocket boosters that let hot gas escape and touch the fuel tank and set off a huge explosion in the fuel tank. But there's a lot of context here that people don't really understand. It wasn't just the design of these O-rings that put these little segments of the boosters together. There's a lot of context. First, the temperatures of the launch that morning, early morning launch, were predicted to be in the low 20s, well below freezing, below 0 Celsius. The manufacturer spent an hour-long presentation early that morning informing NASA managers that they had no data that showed that this booster could perform on that. The lowest temperature they had previously ever experienced was 53 degrees Fahrenheit, quite a bit higher than the 20 degrees. Overnight, it was even close to 0 Fahrenheit, which is very, very uncommon in Florida, where they launched from. And so they argued not argued, but presented a strong case why they should not launch the shuttle that day. NASA managers didn't like that answer, so they hung up the phone and they told Morton Thiokol, "We're going to call you back in 15 minutes, and we'd like to hear, hint, hint, sort of a different answer there." So during that intervening time, the Morton Thiokol engineers beat down, not physically, but figuratively beat down their engineers, and they said, "Hey, now take off your engineering hats. Let's put on our management hats here." And they called back in 15 minutes, and suddenly Morton Thiokol was green, thumbs up, go for launch. And just a travesty of engineering ethics and everything else going on there. So, of course, the cause was not just the O-rings themselves, it was in the temperatures that were launching it, but lack of communication. It wasn't only that day, but back early when the space shuttle was being designed in the early 70s, there was a report that said, hey, if this burn through were ever to occur, there's no way to abort. In 1977, they did some testing of these boosters and pressurized them with water and showed how the joints expanded and the O-rings could be, hot gases could blow by the O-rings. They had evidence as early as the second space shuttle launch of Columbia that they were having erosion of these O-rings because they recovered these boosters after every flight. And then the managers of the booster program from the Marshall Space Flight Center at NASA never reported this to senior management at headquarters. So there's engineers there arguing for a redesign, and the message only got so far up and never went to the highest levels at NASA. One of the commissions that investigated the accident said it's likened to a situation where airline is permitting one of its planes to continue flying despite having evidence that the wings are about to fall off. And the schedule pressure was a huge contribution to this accident as well. There's lots of reasons why they really wanted to get this shuttle off. That year, they had a record number of missions scheduled, over 10, that they'd never flown more than 6 or 7 in a year. They were trying to use this as a case to support budget requests for the flight rate they needed. The launch right before this Challenger accident, there was a record number of scrubs due to bad weather and mechanical failures. They also wanted to get this off the pad so they could refurbish it for the next mission. And that night, President Reagan was given a State of the Union address and wanted to refer to the teacher in space teaching all the children. The military had also given NASA the job of launching military satellites, which is really strange. There's been a few were already launched before the accident, but they had pretty much taken the job away from the Air Force and given it to NASA, so there's a lot of pressure for NASA to try to perform. And of course, the media would always make jokes every time there was a launch delay about the shuttle. So lessons learned briefly on this one was strongly of the lack of communication. Everyone knew better. They had analysis. They had all the engineering memos and tests from years early that were just ignored, and engineers' advice was being ignored, and the risk was not being communicated up the chain. And of course, schedule pressure was a huge factor. The next little mini case study I want to present was the Challenger accident. So fast forward 17 years all the way to 2003. We had the Challenger, the Columbia accident, They had another crew of 7 here, including an astronaut from Israel, a visiting astronaut. And they launched, a beautiful morning to launch, beautiful, successful launch. And they had no idea what had happened on the way up. On the way up, about 82 seconds into the mission, there was a tiny piece of foam that fell off, or not tiny, but maybe relatively tiny to the space shuttle, maybe about 14, 16 inches long, fell off, and while the orbiter was going about 1,600 miles an hour, it hit the leading edge of the wing. And this, of course, is what eventually caused them many days later when they tried to come home. And they found out after the accident that of the 79 launches where they had really good imagery, 65 of them showed evidence of this foam coming off. And unfortunately, it was a lot of the institutional practices and culture that really were the main causes of this accident. There was inadequate concern of what they called deviations of expected performance. And this time, was instead of the O-rings that showed problems, this shedding, in this case, it was shedding of foam from the external tank. They've also cited a silent safety program. So NASA, of course, has hundreds and hundreds of safety engineers, and they do all this analysis, and then they don't really come to the table and make any strong statements. It's like a lot of engineering organizations, the engineers sort of rule the roost, and the safety guys are always the last guys at the table saying, well, I think I have a concern, sir. So they cited this a silent safety program at NASA. And of course, again, like the last accident, schedule pressure was big. This was one of the few missions that didn't go to the space station. So the schedule pressure here was trying to get this one out of the way so they could finish assembling the space station. So this was purely a research mission that did not have anything to deliver, did not go to the space station. They also cited poor safety management. The foam debris coming off the big orange tank had been happening, like I said, nearly every flight. And each flight was interpreted as a reason for diminished concern. So that's why the quote, the normalization of deviation or deviance from requirements in design got cited a lot. So NASA managers and engineers confused good luck in previous foam incidents with predictable and acceptable risk performance. So here's a picture of where the piece of foam came and where it hit the leading edge of the orbiter. And this is pictures of the flight. It was a very successful flight, and God bless them. They didn't know that there was this damage in the wing, and they had a great, successful flight, and they came back, and they took great pictures. They finished all their research, took great imagery of the Earth. And here's pictures of the orbiter, Columbia, re-entering, and there it is breaking up, ironically, over East Texas between Dallas and Houston, right where the astronauts and all their families lived. Here's some pictures of the flight controllers waiting for waiting for the return of signal, and which never came. It was a very public funeral. The president visited the Space Center and had a ceremony there, and of course, an outpouring of sympathy from around the world. And here's the tracks of debris. There was debris scattered over 4 states, and most of it in East Texas, like I said, not too far from Houston. So during the flight, engineers made requests several times to obtain imagery of the orbiter to see if there was any damage from this foam. It was discussed at the highest levels and rejected every time. There was even one flight director that went around all of NASA management, went right to the military, asked for imagery. They started to get it for him, and then once the NASA managers at the headquarters found out, they went and closed that down. So it was very, very tragic, all the things that had happened over and over and over again that were shared with the earlier accident. So lessons learned briefly for Columbia. They believed it wasn't possible for the foam to destroy anything significant on the orbiter, but there was really insufficient evidence and lack of analysis to prove that it was safe. So they just assumed, hey, well, it didn't kill us last time, and won't kill us this time. And again, the quote that is used over and over in this accident is the normalization of deviance from requirements and design. And again, a lack of communication of the risk of the foam. Lastly, today I'll wrap up. I'll talk about the recent Virgin Galactic accident, which one journalist described as a failure of foresight and oversight by the Federal Aviation Administration, which regulated the launch or licensed this as an experimental launch. Just real briefly, just to give you familiarity with the business model of Virgin Galactic, this is a spaceport in New Mexico that was built where they planned and still plan to conduct commercial spaceflight for tourists for about $500,000 or so, 200,000 pounds or so. In the foreground there is the launch vehicle and the spacecraft. So the launch vehicle actually is this plane with two fuselages here. In the middle of the wing, you attach the spacecraft called Spaceship 2, and this is the tourists. It can be, I think, up to 6 or 8 tourists will fit on there. This is the actual photo of it there, and here's the twin fuselage launch vehicle and the spacecraft there in the middle. So the operational concept here is that you launch you take off horizontal like an airplane, like a mini airport, and you would go up to 50,000 feet, which is quite a bit higher than a commercial airliner. You would release the Spaceship 2, in this case it would drop like a bomb in free fall, start its solid rocket motor, oops, sorry about that, launch up into space, which is arbitrarily about 100 kilometers. It would deploy this feathering system on the wings so it would slow it down when it re-entered the atmosphere so it wouldn't burn up. And then you land horizontally exactly where you took off, and you could do this all in about 20 or 30 minutes. Very exciting program. Would be you'd have like 6 minutes of weightlessness, and everybody would have their own window, and you'd look out, and everything was going to be great here. But unfortunately, last year on October 31st, this was their 4th powered flight of the Spaceship 2. It broke up 13 seconds into powered flight. This flight test was very different than the previous 3 powered tests before. It was a brand new engine, new hybrid engine. Instead of burning nylon, they were going to burn rubber. And so there's significant alterations to the vehicle and the spacecraft system. So everyone was on pins and needles. Not only that, there was the planned burn for this was going to be 38 seconds long, which was more than twice as long as any previous test. So it's quite an ambitious test with a brand new motor to go that long of duration. There was, and like the other 2 accidents, there was intense schedule pressure. There was 9 years filled with setbacks and delays, and Virgin Galactic was putting a lot of pressure on the manufacturer and designer of the airplane and the spacecraft, called Scaled Composites, to get that flight test program finished. It was supposed to be done years ago, and the latest date they had was 2014, and Richard Branson and his son Sam were going to take the first inaugural commercial flight as soon as these test flights were over. And everyone, when it blew up, was sure that it was the brand new engine that had blown up, but in fact, found out later that it was not the engine. Here's a little pictures of the sequence of what happened. So it got up to 50,000 feet successfully. The spacecraft separated, the engine ignited successfully, and then for some reason, the wings folded here about 10 seconds earlier than they should have, and then the aerodynamic forces before it went to supersonic regime broke up. Miraculously, one of the pilot, Peter Siebold, remained conscious, and there was a chase plane chasing the spacecraft, and he was thrown from his seat was thrown from the rest of the debris, and they actually stuck his thumb out like this, like I'm alive. He had the wherewithal to separate himself from the spacecraft, and a chute automatically deployed, and he survived with significant injury. The co-pilot, however, Michael Alsbury, we don't know, but we don't think he ever was conscious, and then he perished in his seat without ever separating. Here's a sort of gruesome picture of the spacecraft breaking up. And here's some of the gruesome pictures of the debris that was collected around the desert, in the Mojave Desert. So what happened here? And why the feathering wing and all these kind of things. So first, that day that the Scaled Composites released a statement that just said that the spacecraft had not blown up like everyone said, but it wasn't really clear until 2 days later when the National Safety Transportation Board, the NTSB they call it, found through video evidence that the co-pilot had actually unlocked the feather device way too early, about 10 seconds too early during the power ascent, which caused the aerodynamic forces to rip the whole spacecraft apart. And the feathering system, why did they even have this? Well, back the founder of the chief designer, Burt Rutan from Skell Deposits, did this in response to an X-15 accident back in '67 that killed a pilot, Mike Adams. And he was obsessed with making sure this would never happen to his vehicle. So what happened to the Michael Adams X-15 flight in '67, it came in sideways through the atmosphere and broke up. It was going too fast and couldn't maintain control. So the idea of this feathering configuration was to make sure it slowed down when it started hitting the atmosphere and could maintain control under a bunch of different flight regimes. This singular focus, however, led to less attention on what could happen if the feathering device was deployed too early. The designers just assumed it would never happen, and there was sort of over-focus on this one hazard at the expense of all other hazards. So why did Michael Alsbury unlock the feathering system too early? We'll never know for sure, but here's a picture of the feathering system. It's this huge metal bar, horizontal metal bar here, and you can see on the left picture, this is what it looks like when it's locked. There's actually a detent in there. You have to move it to the right to take it out of the detent, and then move it down about 6 to 8 inches. So there's no accidentally doing this in any way, like bumping it with your elbow or bumping it with your hand. So I put this little graph together. So on a nominal flight, what would happen is you'd separate, would be the powered flight of just the spacecraft. So you would release, you'd fire the engine, and as you would go through, the co-pilot's supposed to call out Mach 0.8 and just keep the pilot aware of the situational awareness of what's going on. So you would transition through the Mach supersonic regime here, and then miraculously, the co-pilot's job was to make sure that he didn't deploy the wings didn't deploy before Mach 1.2, but he would have this small 3-second window, or actually probably 2.5-second window from Mach 1.4 to Mach 1.8 to unlock the wings. And if he did it too late, you'd have too much speed, and you'd come in if the wings weren't capable of feathering, you would die at Mach 2.0. And if you did it before that, obviously we found out what happened. So for some reason, he didn't wait till Mach 1.4. He deployed them way back here after this call out. So he was seconds and seconds away from ever getting into the regime where he should have deployed these wings. But the reason I bring this up is because there was such a tiny window where he was supposed to deploy these wings, which would have been a hard, difficult task in any situation, even given a nominal flight. The NTSB said the probable cause was failure to consider protection against the possibility that a single human error could result in a catastrophic failure. The other things that they cited were he hadn't flown for about 1.5 years, and he had not had no recent experience, with the G loads and everything else. So obviously he was way obsessed with not aborting the mission. If you got to back on this chart, if you got to Mach 1.8, you'd have to abort the mission, and you'd have all his data lost. So, pilots want to make sure they don't screw up and, cause the failure of the mission. So he's obsessed about this 1.8 thing. I guess he decided to be really conservative and deploy it there, but well before even the supersonic transition, which obviously was catastrophic. Findings where the Skell Deposits approach failed to account for all possible failures. They did not meet all the FAA, the Federal Aviation Administration permit requirements, and did not identify human or software errors as causing hazards. Other stressors, we're going to talk this afternoon about 4:30 or so about human error, but there was no cue cards, no checklists used, which pilots typically use in just about every application from spaceflight to aviation. Things had to happen so quick there that they memorized their tasks instead of writing them down. Again, they were worried about this 1.8 boundary not to abort the mission. And again, the operational experience was cited of not having experience in flying in this spacecraft for 18 months. So whose fault was it? And obviously there was a human error involved in this one, but as has been said in the literature, human error or mistake is often a symptom of a flawed system. And I think I would agree with that. There was no design, no safeguards to prevent him from unlocking this thing too early. There was no manual procedures. What, 5 minutes? Okay. There's no manual procedure that that warned him, like, do not unlock this, in this regime or anything. The simulator training did not replicate the environments, and of course that's hard to do, so that one I didn't really highlight there in yellow. But the hazard analysis did not consider pilot-induced hazards, and that's something that is just hard to believe that would happen in this situation. So in summary, for the Virgin Galactic, really what it was, in my opinion, was just a lack of system safety, a lack of thorough hazard analysis, an incomplete or really a non-existent human error analysis for this, which should have been a relatively simple flight as far as what the pilots have to do. Certainly not anytime you're going supersonic and traveling into space and back is not simple, but the tasks that the pilots had to do on a nominal flight are relatively simple. So they should have had that human error analysis completed. An incomplete fault tree analysis with unmitigated hazards. So the Federal Aviation Administration found that they had done a fault tree, but then they just assumed the mitigations were all accounted for, but they realized they just accounted for these different failure scenarios and they didn't mitigate all these hazards. So generic lessons to all three of these cases, in summary. We have to keep questioning the performance of the vehicle and looking for unidentified hazards. We have to define what we mean by acceptable risk, demonstrate we have sufficient confidence in our safety and risk analysis to determine acceptable risk, and then respond appropriately to findings. And that's the hardest part, is a lot of these accidents, obviously hindsight is 20/20, but so much evidence laying around of what could have happened or what was about to happen. And this is a tough one. Engineers, operators, management, we all need to preserve our ignorance and remain humble. So like we've talked this morning about in the medical industry and other things like that, people, when you've been in this industry or any industry for too long, you think you know it all and you've seen it all, and you must remain open to new ideas, new information, and preserve your ignorance. And when new information, or maybe it's old information, is represented over and over, maybe you should pay attention and say, well, maybe there's something to this, maybe I should stop and pause, look at that in a new light. So again, to summarize, for the Challenger, it was clearly a lack of communication of known risks. They knew better, immense schedule pressure, and of course in the case of the contractor and the management at NASA, leaning on them, lack of ethical behavior and just ignoring their analysis. For Columbia, it was a lot of ignorance of just insufficient analysis, and they couldn't prove it was safe. At NASA, we always have to make sure you prove it safe. You don't have someone come into the room and say, well, prove to me this is dangerous. You have to prove that the operation you're doing is safe, and that should be the same way, obviously, for whether you're mining coal in an open cut or an underground mine or working in a hospital. You have to prove that what you're doing is safe and have some analysis or some data to back that up. The normalization of deviation and lack of communication. And then for Virgin Galactic, like I said, it was just a total lack of system safety. And so these are a lot of underappreciated hazards. And in summary, all the serious accidents in the history of human spaceflight are due to the failure by the community to recognize and appreciate the hazards and risks involved. I'll close today with a short excerpt. This is an excerpt from the movie Apollo 13 with Ron Howard, you guys might have seen. This is after the Apollo 1 fire that happened in the late 60s in 1967. This is where one of the astronauts is brought up in front of a congressional panel doing congressional testimony, and the congressmen here are drilling the questions into him. But you'll see that this really applies to all of our industries. It applies to the three accidents I've mentioned today and a lot of stuff what we do today. So we'll dim lights and I'll hit the play button here.
It just took me a minute or more to tell you all that. In actuality, from the first mention of the fire to the rupture of the hull, only 15 seconds went by.
Colonel, what caused the fire? I'm not talking about wires and oxygen. It seems that some people think that NASA pressured North American to meet unrealistic and arbitrary deadlines, and that in turn North American allowed safety to be compromised.
I won't deny that there's been pressure to meet deadlines, but safety has never been intentionally compromised.
Then what caused the fire?
A failure of imagination. We've always known there was the possibility of fire in a spacecraft, but the fear was always that it would happen in space when you're 180 miles from terra firma and the nearest fire station. That was the worry. No one ever imagined that it would happen on the ground. If anyone had thought of it, the test would have been classified as hazardous. But it wasn't. We just didn't think of it. Now, whose fault is that? Well, it's North Americans' fault. It's NASA's fault. It's the fault of every person who ever worked on Apollo. It's my fault. I didn't think the test was hazardous. No one did. I wish to God we had.
Okay, thank you. That's all I had for today. Thank you.